everybody. Welcome to the second ME Research Seminar of the fall semester. So today we have Nana Adoo, who is a PhD student in material science, who is doing research with Dr. Bruno in the ME department. So Nana, let me hand it off to you, and we'll go for you have the balance of the hour. There's maybe some time that you could allow for questions. And then also, as we did last week, we're gonna, after we adjourn here, we're gonna go over to the CM 215 room, the ME Zoo, and there'll be some drinks and light refreshments and some socializing. All right, thank you.
Well, good afternoon, everybody. And like you said, my name is Nana, and I'm presenting on a microstructural processing of phase stabilization of off-stoichiometric iron manganese gallium shaped memory alloys. So my advisor is Dr. Nicholas Bruno, who is, of course, at the mechanical engineering department. You all know him, I guess. So this is going to be my outline. I'm first of all going to introduce you to what shape memory alloy materials are, what qualifies a material to be called or known as a shape memory alloy, why iron manganese gallium, and how useful is it to us actually? Why should we be more concerned about this particular shape memory alloy? I'm going to talk about what has been done or what is known about these materials, and also discuss what has been done, and of course share some results and conclusions with you so far. So without much ado, shape memory alloys are actually they're a special kind of materials which are made of metals as well. You know, alloys are metallic mixtures or metal composites actually. So they have this they actually demonstrate super elasticity and shape memory effect actually. So then I can define them, or we should know them as materials which actually demonstrate a reversible solid to solid phase transformation materials. So this is it. And there are so many of them around. The first person to actually have identified this kind of material was Ilako. I think he was working with MIT in the 60s when he discovered this. And after that, several of them have been seen or found. They're in the group of nickel, manganese, gallium alloys, or iron-based alloys, copper-based, copper, aluminum, and so much of them. So, sorry, yeah. So these are the characteristics I'll be talking about. And not sure. Yeah. So, I guess how to do it. Yeah. So yeah. So sorry about that. So these materials are actually when subjected to a stress, they kind of deform, or they show this reversible super elastic transformation process. As you can see with this animation ongoing, you could see the whole thing is shaped. I don't know if it's working, but yeah. So
what do you mean by super elastic?
I'll define it as I go up. Yeah. So you can see as these materials are subjected to these stresses, which could be stress as in pressure, as in magnetic field, as in temperature, they kind of react to these material. They kind of react to these environments you have or conditions you have subjected them to, and then they kind of they show some transformation from one state to the other. And the states that they usually transform are from the austenitic phase of metal to a martensitic phase. They are metastable. And these what makes them metastable is the martensite, the presence of the martensite in there. And these martensites are actually they are shear dominating, and then they are lattice distortive. And so between they are they are shared they are shared deformative by how do you call it, the process that they are going through, because there's a shared process going there, and then they distort the lattice formation or the lattice definition of the material. So this is what actually happens when you subject them to heating or something, or an electric field. These materials undergo these stresses, and then they kind of move from one state to the other. So if you increase in, for example, if the stress is by how do you call it, pressure or something, you kind of see them reacting or obeying, or they how do you call it? They obey or respond to these stresses by increment, and that is actually get to a certain stage that they have to transform, or they transform and then they use heat to the environment, get to a point, kind of take up the heat again, and then recover back to its original state. This is what we call the superelasticity, and the temperature change actually is the recoverable ship recovery state, where they kind of remember which state they were in, and then get back to this how do you call it, original shape. And increasing is the superelasticity, because they have the lattice distortive process. They kind of expand elastically, and that's the superelasticity by an induced strain that is in there. And then the recovery is when you have to induce the temperature, and then they get back to its original state. So if you saw this video, the stresses actually was going this way. When the stresses are actually expanding, that is when they are advancing or responding to the pressure. If you follow the same procedure here, or the same graphing here, you realize that from A to C, actually there's a constant from 0. That's when the constant stress is being applied. It gets to a point they cannot actually take it any longer, and then they kind of get some entropy change there, heating, and then shed off that heat by exothermic reaction, and that's a latency. They lose heat to the environment in a way, and then they have to, by natural phenomenon or natural equilibrium, they want to return back to the original state. So if you just induce the heating, or if you induce some energy to it, it gets back to its original shape from C to D, and then back to 0. So in the same way, it's like it's now playing there. So you kind of now give it another heat, and then it responds to its original shape. So SMAs are actually, or shape memory alloys, are so useful in the sense that with this recovery and superelasticity, you could actually use them for so many things. You could use them for how do you call it, bimetallic strip applications. You could use them for semiconductor applications. You could use them for semiconductor applications. You could use them also for mechanical recovery applications as well. So based on the kind of force field you are inducing them to, or you're using to drive that shape memory or shape recovery process, you could actually have it in a uniaxial form, or compressive stresses. This we call the elastocaloric effect, because of the heating that gets involved with it, or is coupled to it. If its pressure is barometric or baroelastic, barocaloric effect, and then magnetic field, of course, will be the magnetocaloric effect as a result of this heating. Now, iron manganese gallium is a ferromagnetic material, in the sense that when you induce it to a magnetic field, it aligns all its magnetic axis to it, and then that shoots up the energy, or ramps up the energy, and we call it a magnetic. It increases the magnetism of the material, and we call it, induces a magnetic field induced strain, which is larger and shares of a large heat because of that. So it's coupled to some it's coupled to the heating, giving it more energy to get out. And so we have large MCs, which is the magnetic caloric effect, as well as the field-induced strain. So looking at these processes that are happening, we could actually, there is a way, or there is the need to actually quantify how much energy these things are actually giving out or actually absorbing. And the way we can relate these things are from using Maxwell's equations, which are from the top there. Right. So the first level actually is Maxwell's equations, which are actually relating the state functions in their exactness into the phase transformation stages based on these adiabatic and thermodynamic processes that are going on into the phase transformation stages, where we kind of, from the exact relations of the state functions, how they change into one another, into the Clausius-Clapeyron equations, actually in the isothermal phase, we try to align, or we try to relate the exactness to the thermodynamic functions, and try to quantify what's going on in there. So if it's pressure, we know the entropy change there. The entropy change there is related to a strain by temperature, which is actually the parameter which is isothermal, or which we relating as constant, and under the constant stresses as well, where the deformation becomes it takes place at a constant pressure. So we relate those ones to get isothermal entropy change in it. In the same way, when it's pressure, pressure. In the same way, in pressure, you are looking at temperature, volume change thing. You need to relate them and then get those relations. And then when it comes to magnetism, it's the field as well as the temperature. So this is what is going on, and this is what I have been trying to quantify over the years, over the months. So why iron, manganese, gallium? A lot of these materials exist actually, but iron manganese is more like when it's a metamagnetic material, it shows a magnetic phase at one point, and it shows a paramagnetic phase at one point. In essence, when you heat up this material, it has a tendency to actually demonstrate paramagnetism. And paramagnetism means it doesn't actually obey any field or respond to any field. At the same time, it can actually behave as a pure permanent magnet when you have its axis aligned to the soft field with the field axis of the field, that the soft axis of the field that you're actually inducing it to. It also demonstrates a large magnetic field induced strain, as I said previously, and also, also it's characterized by these phase changes from either switching from a ferro to para, or from a para-austenite to a ferromagnetic martensitic stage. So this is all because it has that characteristic martensite in there. So how do you use these materials, or how do you actually apply these materials in our day-to-day life? Because of this heat exchange effect, you have a solid-to-solid supercooling effect going on. In other words, you can, because of the heat exchange, you can use it to replace coolant, refrigerant coolant, and use it in supercooling applications. Get rid of the CFC coolants in refrigeration, and that's one thing we are looking at doing. Another thing is to apply it in the sense that because you apply a little energy to it, and you see a large effect on the opposite side, and you can actually use it to induce energy in systems, and then serve as an energy harvester. So, yeah. And in systems where you have energy conversion from one state to the other, when you incorporate these systems in these materials in there, because of that solid transformation which is going on, actually it increases the coefficient of performance, which is actually a relation for the internal energy input to the work output of the system. And it by research, it has been shown that these materials, when they were incorporated in such systems, bumped up the efficiency of the systems up to 175%. So what's the problem here, and why am I actually so much interested in these things as well, or working with this and not what has been done already? The issue is, despite its propensity being used as these materials for these things, we have a large hysteresis problem. There is so much losses in these materials, especially iron, manganese, gallium, when you compare it to the others, in the sense that you have thermal and then transformational losses. And it doesn't really appeal more looking at the advantage of these systems. So despite we knowing how, let me put it this way, it appeals very much when you just look at the results it gives, but it has its consequences as a result of having a large input of energy into it before it can respond. But if you're able to minimize all these effects, then it becomes okay or very appealing to use for these kind of applications. Nickel-based materials, or these materials for shape memory alloys, most often, because of this FCC to PCC, they're very brittle. So you cannot actually engineer it. It's not easy to engineer them in these applications. Why iron? Iron has been found to be ductile. And if we can actually minimize this, then we can use this in these applications that we're talking about. So there's this researcher called Zhu, who found out he found out a lot when working with several of these compositions with iron, manganese, gallium materials. He realized that on the crystallographic level, when these phases, when these transformations were happening, he saw that there was there are some mixed phases of the phase-centered austenite, which is mostly the parent, moving into the body-centered martensite or tetragonal phase. He saw this actually was the problem. If you have mixed phases, you don't necessarily exhibit, or the material does not necessarily exhibit that phase transformation. And so he tried to figure out which compositions were actually okay for the phase transformation or the reversible process. And he drew out this map where you could see in the mapped region within the ternary phase diagram is materials or the compositions he found which were basically demonstrating which demonstrated the reversibility or recovery of these materials. So what have I been doing, or what this actually served as a very good stage to start my work from, and what I've been finding out so far. So with respect to other works which have been done, there since 2009, this guy Omori and his group actually found out that if you have these materials, the iron manganese alloy materials, the transformation was actually from a BCC to a BCT, which guaranteed your phase transformation to go on. And he found this within this composition range. This composition and the compositions are actually guided by a valence to atom electron ratio, or in other words, you have to have an electron density before you could actually get these things in a position where, or in a map where they're going to work. Another researcher which I just saw was also Zhu et al. He actually found out the mixed phases, and so and also he was just doing an experiment and realized that around a certain magnetic field, he could actually bump up his he could actually realize a high magnetization up to 98 electromagnetic units per gram, which was one of the highest in this materials he worked with. In 2011, this forward transformation, magnetic forward induced field transformation, phase transformation, was also realized by Omori again. And this was actually when the phases were being transformed from the FCC to the BCC and then back to a BCT. This is what he got. And then Ma et al., who worked on iron-based manganese alloys, also found these systems going on. It's either from FCC to a BCC, FCC to an HCP, or BCC to an FCC. One thing that he found which was interesting was that FCC materials to BCC transformations were not actually were not actually known and were not actually a lot in this field. But he realized that with this, actually, what he found was it wasn't useful, because if any time he did a composition and he found out from the XRD or whatever, they really did not mean or define the transformation bandwidth within the material for him. So with this, with these papers and a lot more I found, it was quite clear that there was no definitive transformation crystallography for these materials. So in order to actually get one which will tell you that surely you can actually have this composition transforming or demonstrating the magnetic shift memory alloy behavior, I am taking it upon myself, or it's actually good to research, get this electron density bandwidth, which is more probable to show these materials going to transform. And so I came up with an experimental plan to start this whole thing by actually looking all through the literature of the materials which seem to transform by the data they produced, got all of them, and then started getting the hysteresis from all of them, calculating the hysteresis. I came up with this iterative process by actually sampling them within these 10 sample bandwidths, going through a solution heat treatment, and then using these characterization techniques for to come up with my analysis, either is through EDS, XRF, and then ICP, from which I will use those the XRD actually to confirm a lot of the phases that I'm looking at. So why the iterative process? There's so much data out there, and I want to narrow down on what works. And what works actually is best proven when you keep doing something and then narrowing down on them. And it's efficient for me. It's time consuming, and then takes out every confusion that I look at. So to go through what has been done, I'm looking at the material processing itself, which is through a solution heat treatment after an arc melt has been done, through how do you call it? An inert system, creating an inert system which I sort of isolate the metal from any external environmental inclusions like oxidation or anything, and then through how do you call it, heat treatment, I'm able to get the material to homogenize after the arc melting, and that's the process. I do this with I have done this over the months with argon, and then under a pressure of 0.09 bar, and that is what I have actually been able to do so far. The titanium sponge being used here is actually a control which will make sure and ensure that there is no oxygen in your system, and to ensure that those materials are bound to what transform once you are done with the treatment. So without without making or delaying in these processes, I actually try to minimize the time frame between the heat treatment and then the quenching process. And it had to be done, or it had to be very fast, because if you could do this early enough, it could actually ensure your conversion between one crystal structure to the other, which you are actually looking at, getting the transformation you really need. So the arc melting was done, everything was done in-house here except magnetic measurement. So this is a picture of the arc melting system that I used, and it's a new system in the MES building. What's being shown in here is the closed and then the open. So I got 99% purity, 99.9% purity of these granules, iron, manganese, and then gallium, based on calculations to get me my E/A ratio in the bandwidth that I shown between 6.15 and then 6.55. Measured everything, calculated, and then put them in the copper chamber there, and then arc melted it. The copper chamber is this, you see, is the open pot in there. And then the arc melting is actually with a rod up there on the gear. So I don't know how this works, but so let's go on, and then yeah, I think I gave all this information, and then after that, this is the process that I said earlier on. The atmosphere and the environment is actually a controlled one, and then with the pressure in there, which is also known, we actually looking at re-engineering everything. So despite you having arc melted it, it doesn't mean that everything or all the system you have is homogenized, you know. So to homogenize it, the heat treatment is essential. And these are systems, these are the processes I went through by using this arc melting system, gas touch, and glazing in a coarse tube to ensure that the environment is included. And then, yes, that's one thing. So this is a melted and sealed alloys in the quartz. And I have a short video for you in the whole process. So once you get the blazing, the gas touch lighted, you actually heat the quartz tube until it starts to melt, or the atoms begin to dissociate, and then you start to twist it, and then seal it off after pumping in or flooding in some argon or some gases to, yeah, and then that's it. So, yeah. So that was the sealing process, and then the oven I have used over the years is this one. So you have it open there. It's actually up to 1,150 degrees. So um, that is it. And this is the quenching, and the quenching was done in ice cooled or ice water cooled bucket. And then from here, once it's sealed and heat processed, we actually get it ready for a squid measurement. And this is the squid which I used. It's not in the school here, it's in SDSU. So I had to go to Brookings to take those measurements. So this is the results so far I have been able to do or get. Well, I will start with the composition process or composition from the arc melting. So the map here is just like replicating or trying to figure out what you did, match it with mine, and see whether I'm actually doing something right or not. So all the processes, all those things there, with the exception of the S ribs, are actually what I arc melted. The S ribs I'm using as a standard, which has been done elsewhere in an external lab. So I did the same thing and then measured with mine with the data acquisition techniques we have here to see whether it matched theirs. So to have the confidence in what we were doing. And this is actually what it is for the ribbons. The test, external test, and then the in-house match test actually shows what's in the circle there. So this shows the reliability of the in-house data. Now, to get these phase transformation data, it is not only by magnetic interference devices. You can actually use a DSC, which is differential scan calorimetry, which it takes specific heat capacities of these phases, and then shows you the differences as and when you go along. So from what I showed you in a square, you're actually looking for a start temperature where one phase begins and a finish temperature. So the M's and the A's are denoting the magnetic start and finish, and then the austenitic start and finish temperature. So for a DSC or thermogram, you could see that when I tested the material, it got to a point when cooling, it's a heat and cool experiment. So when I heated it to up to a 200 Kelvin, 400 Kelvin, sorry, it actually, there was nothing happening, but as I cooled it below subcooled, you could see that there's something happened. And the discrepancy here begins here, which is when the heat coefficient actually changed up to this stage. And then when I started heating back, just before the zero, you could see that in the heating, which is the austenite phase, you could see that it's also showing there. And the preliminary results these are the preliminary results I did for the ribbons, and then tested them for two of them. I had 4 ribbons. I tested 2, and they all showed this transformation. And then I plotted, I did a squid test on them. These were actually sent to another external laboratory to test it. And you could see very large hysteresis in there, as in when the field was rammed, you could see the band widening, then drifting to the right. And one thing for sure is this, that whatever is being confirmed, whatever is being shown here is being confirmed on the squid, as in when the transformation temperatures begin. And you could see from these bends, this is a heating and this is a cooling. So you cannot go this way, and then in a kink here, you could see the starting temperature here, which is in the heating zone, where these tangents actually meet is one of these temperatures, which is the austenite. And then when you're cooling, when you cooling, it starts here. I don't know which one. So let's use the green then. The bend here and then the intersect relates to this cooling here, which is starting here, and then here is the finish of this thing here, which is also related to this particular temperature. And so the range between this and this is the martensitic transformation, and the heating becomes the austenite transformation range. Yes. And so DSC temperatures actually match the squid and confirmed also the transformation ranges that we were looking at. So to get the hysteresis also, I looked at, so to get the crystal phases, or to confirm the crystals that were actually being generated within these regions, the austenite or the martensite regions, I looked at XRD analysis, and XRD will show you which kind of crystals are forming, and the technique actually uses X-rays. By subjecting X-rays to it and looking at the crystal reflections, you are able to know which ones, by their structural factor, matches either an FCC or a BCC phase, crystal phase. And looking at these for the ribbons, I could see some BCCs and FCC mixtures in the transformation. It is not definitive though, because it is only one. The transformation process is actually from, as I said before, was from a BCC to a BCT, which is definitive for this to happen. If you see here, it's a mixture of FCCs and it's a mixture of BCCs as and when you go along. And it's a work in progress still to find out which ones happen. And so this is kind of where I am now, and I'm still going to do that. To make sure to get the orientation of what we're doing from the test so far, I got a single crystal and tested it and got to know where the peaks are, and which is also a BCC shows the single crystal actually shows the BCC, pure BCC transformation, for me to actually know what is happening there and correlate it. So going forward, my next goal is to pick these peaks, match them, or revisit the XRD, and then see which peaks we're making producing the noise. And so the same procedure was tested for the arc melts, and you could see a mixture of phases also. So to get a clear understanding of what was going on, the bulk samples were milled. I actually milled them so we could actually have them in little or small sizes, because the grains were, because of texture for the arc melt, you could actually not have some of the reflections showing. So the powder would actually, the powder was an idea, or was a method to get every one of the peaks showing. But surprisingly, all the peaks that showed there matched an FCC, which was not definitive. So going back, I went, I took the textured material and then XRD'd it, got these BCC peaks, which are conflicting as well. So these two cannot be the same, because we're talking of one material. And this is where, at this stage, tells me that there is something that isn't right here. even though I'm getting my results, I need to clean it up. So the arc melted samples for a pure squid showed one thing. This is a pure transformation for one of them. Another problem I saw was that you see these are two materials, two same materials, arc melted and everything. One squid failed, the other one did not. Why? Because there was a how do you call it, a bomb in the squid data acquisition, and to repeat the experiment, it failed again. I sent in another batch to actually replicate the experiment and to make sure that there is repeatability in the whole processing that we're doing, and it came out right, mimicking the first one, which was actually in the when the field was bombed up to 3 Tesla. So it showed you this, and on the fourth sample, and this is the fourth sample, the interesting thing that I found also is that I could get hysteresis as low as 52.4, and that was really interesting because in all these materials, the range of hysteresis I've been seeing was between 80 and 90. And so this was really an improved or significant change in whatever I'd seen or I'd done. I failed in some of them. Two of the ACMELs actually succeeded, and then 2 failed. And these are the failed tests in the bottom. So even though they magnetize, they do not show this shape memory or transformation effect. You could see, and it doesn't mean they couldn't be used for other applications, but for the purpose that we want, it won't work. So then I also measured those hysteresis, and you could see some of them produce very large hysteresis, and then others also very low, but they all failed. For this, which was the one that succeeded, which is the first one, I'm measuring around 90, which is matching with literature. And then the others which failed, even though they had no, the other which I previously measured was around the 50s, which is the second one, the fourth one, this one. I looked at why these materials were not, some of them transformed and then some did not transform. And by that, you would have to look at the micrographs. And to look at that, I started with the condition of the sealed or the annealed. And you could see there's enough texture out there for the arc melt 1 and then the 2. And with the 2, you could see some acicular structures which look like martensites. And martensites are actually pin-like. They're strong, they grow orthogonal to grain boundaries. And looking at these, you could also see some features of those things, but this material failed too. So the fact that there was martensites in there did not guarantee a phase transformation. Arc 1 had a transformation and hysteresis, a very large hysteresis, but you don't even see martensites here. And why? Because the transformation temperatures are actually so low, so you don't expect. 2 is showing you, which is even at room temperature or something similar to that, but you don't see any transformations. And Arc 3, very fine grains, hexagonal by looking at it, but there's nothing showing for that. And this was one of the hardest materials actually I encountered when I was cryomilling. It's not ductile, very brittle, but very hard as well, so never transformed. And then the one that transformed showed this one as annealed. To go further into it and try to figure out what was happening, I did a backscatter image analysis, which is by the EDS, by the SEM. Try to get you contrasting images based on atomic different atomic number differences. So large atomic numbers will actually appear bright for you. So you could see in arc 1 that there is homogeneity in the sample. You could see the phase grain sizes and then everything matching out there, same. But when you come to the second arc melt, you could see these matching sites showing in there. You could see those circular structures. You could see them from the grains going there, but never guaranteed any transformation. 3 had these grain texture. It did not actually show just like the annual sample, but there was no transformation as well. And then at 4, which transformed and produced better results, did not also show those Martin sites. Of course, we don't expect to see it at this temperature unless we subject it to a subcooling to see those structures forming here and see it. Yeah. In all these, you could see cracks, except in Act 3. It tells you that they are still brittle, and there's a way to actually minimize that as with your homogenization processing. So looking at my failures success so far, I had to look at devise another way or devise a plan to get what I wanted. Over the past days, I had gone through this process and I had seen BCCs showing, but I've not been able to stabilize them. The question is, how am I going to stabilize this to guarantee that whatever material I'm producing is going to give me the least optimal hysteresis as well as guarantee a phase transformation where these the shape memory characteristics could be seen. So far, I've worked on 4 and I've gotten 1 showing the best result. I'm still going to go through the iterative processing going forward, and this is the next move I am looking at. The major thing I found was the quench rate, or the process from the oven to the quenchant, which is how do you call it, a large determinant of my success moving forward. And with that, I've come up with this process where I'm just going to pick what worked and then subject it to these tests under 3 gases. Why? Because every gas has an effect on it. We're trying to see what it is, and we're doing it in vacuum without any control, and then in helium and then argon. We have a result for argon. We're going to see if it still works under 2 different pressures, and then see what the results are going to be like. So at this level, we have IWP, which is the ice water quench, and then the super quenchant, which is a solution of brine and other chemicals. Why are we using different quenchants here? Is to induce a lot of boiling around it, and then increase the rate of the cooling for the material as it comes into contact with the fluids. The quench rate is an important parameter going forward to get us our results. If you can't quench fast, there is no point actually going forward with this whole research. So this is where we are so far. So far, I think we had some phase transformation. We successfully characterized some of these materials to a greater extent. And then we have also identified some phases. It says that we still need to stabilize them. I would like to now acknowledge Krell for funding this project, my advisor, and Dr. Jasky from MES, Dr. Peterson, who is here, then Lali. Well, of course, I couldn't do this without the help of ME technician that was. So with that, I come to the end of my submission.
So let me recognize that we're at the end of our time period, so it's 2:50, so if you need to go to whatever's next, that's fine. There's probably a couple of minutes for you to field questions, and then at 3 o'clock we'll migrate into this for some light refreshments. But I don't know if anyone has any questions.
On your SDN images, show those were all backscattered?
Yes. These are backscattered images.
Did you collect EDS from the same areas?
Yes.
Do you notice any? Would you expect a compositional difference between the margin side phase and the partial? No. Because normally contrasting is associated with pump number. One is higher gallery versus aspirin contrast backscatter. And normally, if you can see that in backscatter, typically you can also see the composition.
I did EDS, but I did an area scan, not a point scan. And I think I would do a point scan or a line scan along these space transformations and see what's happening there.
I got one more. It seems like you have a lot of variables that you're testing for. On your last slide, I think you had 12 parameters. So, for your two variants out of pressure and gas. And then if you were to do any replicates of those, it seems like you have a pretty large volume experiments to run. Have you considered doing something like a design experiments to maybe cut down on your total number of samples there, or you nail down the process?
I think I started with 4 and I'm now working on only 1.
Okay.
After I narrowed. So on the 1, I'm able to divide it and then make sure I'm doing all these. Before I decide, if it works successfully, then I'll consider the other compositions that I haven't yet done. There are 2 more compositions which I'm yet to ACMEL test because in literature they also recorded very low thermal hysteresis. So, yeah.
So if there are no more immediate questions, we could stop here, give Nana a round of applause, and then move over to this. Thanks, Nana.